invertible function. It is a very important definition. Okay. So in part D under 5 mark section, question number 39 under 5 mark section is a must question. Let us see the definition. If f from A to B, from set A to set B is a bijection means 1 1 and on. F is a bijective function from set A to set B, then a function g from B to A, domain and codomain gets interchanged. G from B to A, which associates each element y belongs to the codomain to a unique element x belongs to the domain, such that f of x equals y is called inverse of f. That means f of x is equal to y means if you shift y to the other side, f inverse, that is denoted as g. X is equal to g of y. This is implies and implied by statement. F of x is equal to y means x is equal to g of y. The inverse of f is usually denoted by f inverse. Okay. This is one definition. The other way of defining invertible function, or a function f from x to y instead of A to B, f from x to y is defined to be invertible function if there exists another function g from y to x to y is y to x, such that GOF is identity function on the set x. GOF, composition of f and g, is identity function on the set domain x, and composition of g and f is identity function on the set of domain y. Okay. So GOF is identity function on the set x and fog is identity function on the set y, which is the domain of g. Here identity function on the set x, which is the domain of f. The function g is called inverse of f and is denoted by f inverse. So to show invertible exists, it is enough if we show composition of f and g is identity function on the set x, which is domain of f, and composition of g and f is identity function on the set y, which is domain of g actually. Okay. Some standard results, some important results. The first one, it's an exercise. The inverse of a bijective function is unique. There exists only one inverse for any function. You are supposed to prove that. Proof. Let f from A to B be a bijective function defined by f of x is equal to y for all x belongs to the set A and y belongs to set B. If possible, actually not possible, if possible, let us assume there are two inverses of f, say G1 and G2. So we are contradicting that G1 and G2 are equal, they are not different, they are same. That is how we are going to prove it is unique. So if possible, let G1 and G2 be two inverses of the function f. That is G1 from B to A, f from A to B, inverse of f G1 from B to A defined by G1 of y1 is equal to x1 for all x1 belongs to set A and y1 belongs to set B. Another inverse of f G2, let us say, from B to A defined by G2 of y2 is equal to x2 for all x2 belongs to the domain A and y2 belongs to codomain B, are two inverses of f. ಎರಡೆರಡು ಇನ್ವರ್ಸ್ಗಳಿದೆ ಅಂತ ತಗೊಂಡು ಅವೆರಡು ಎರಡಲ್ಲ, ಎರಡು ಒಂದೇ ಅಂತ ಪ್ರೂವ್ ಮಾಡ್ತೀವಿ. ಸೊ ದಟ್ ಇಟ್ ಈಸ್ ಯುನೀಕ್ ಅಂತ ಕನ್ಫರ್ಮ್ ಆಗುತ್ತೆ. ಫಾರ್ ದಟ್ ನಾವು f of x1 is equal to y This implies x1 is equal to definition, as per the definition, x1 is equal to g1 of y, say someone, because g1 is inverse of f we have assumed. Also, f of x2 is equal to y. This implies x2 is equal to g2 of y, say some 2. Since g2 is also inverse of f we have assumed, So clearly, f of x1 is equal to f of x2. See, f of x1 equals f of x2. Both are equal to y, Okay. f of x1 equals f of x2 implies x1 is equal to x2. Bijective means it is both 1 1 and onto, f is bijective means. So f is 1 1. So that f of x1 equals f of x2 implies x1 is equal to x2. But what is x1? g1 of y. What is x2? g2 of y. See, I have written here g1 of y equals g2 of y. So that means g1 is equal to g2. But we have taken, there are two inverses for f. But here we arrive at g1 and g2 are not different, they are same. That means unique. Okay. If possible, not possible actually. So g1 and g2 are not two inverses, they are one and the same. Hence, inverse of a bijective function is unique. The second result, if f from a to b is a bijective function, and g from b to a is the inverse of f, then composition of f and g is identity function on the set A. We are operating f first, we are operating f first. So that means domain of the function f, identity function on the set A, and fog is identity function on the set B. Because since you operate g first, domain of g is b, that's why identity function on the set B, where I of a and I of b are the identity functions on the sets A and B respectively. Solution: given f from a to b be a bijective function defined by f of x is equal to y for all x belongs to a and y belongs to b. Also, g from b to a is the inverse of f. So by definition, f of x equals y means if you shift f to the other side, f inverse, that is g of y is equal to x. G of y equals x. Now consider x belongs to a. X belongs to a means you are supposed to operate f first. So gaf of x is equal to g of f of x. What is f of x actually? F of x is equal to y, So but g of y is x. That's why gaf is an identity function on the set A. Since we are operating f first, domain of the function f is the set A, identity function on the set A. And for all y belongs to b, y belongs to the set B, fog of y is equal to f of g of y. What is g of y actually? X. So f of x. F of x is what? Y. So that means fog is identity function on the set B. Since you are operating g first, in the function g, the domain is the set B. That's why identity function on the set B. Third one, worked example. If f from x to y and g from y to z, x to y and g from y to z be two invertible functions, then gaf is also invertible. Gaf is also invertible with gaf of inverse is equal to, so f inverse composition g inverse. That means g inverse composition f inverse. So to prove gaf whole inverse is equal to composition of G inverse and F inverse, it is enough if we show this one, that is a composition of G inverse and F inverse with composition of GOF is an identity function on the set X. Identity function on the set X. We are operating F first, so domain of F is X, the set X, and GOF, composition of GOF and F in G inverse composition F inverse is equal to I of Z. Identity function on the set Z. G inverse means G is Y to Z. G inverse means Z to Y, identity function on the set Z. For that, consider this composition of GOF and G inverse F inverse of X is equal to F inverse composition. I just group these two. G composition, G inverse composition of F of X. But composition of G and G inverse is, since you are operating G first, in the set, in the function G, domain is Y, identity function on the set Y. A inverse into A is I, that's like that. So F inverse composition, F inverse composition I, if you multiply identity with any function, we are left with F inverse only. Composition F of X. So this is again composition of F and F inverse is identity function on the set X. So for the function F, domain is X, that's why identity function on the set X of X. Therefore, this and this is equal to identity function on the set X. Say some one. Also, composition of G inverse composition F inverse with GOF is of X is equal to G of, I just group these two, F and F inverse I'll group, G composition, F inverse composition F, composition G inverse. So composition of F and F inverse is nothing but identity function on the set X. So GOF of G with identity function is G only. So again G inverse composition G. Again this is an identity function on the set Z. Identity function on the set Z. G inverse means Z to Y, identity function on the set Z. Okay. So this is I of Z. Call it as equation 2. From 1 and 2, GOF whole inverse is equal to F inverse composition G inverse. G inverse composition F inverse. Fourth one, an exercise problem. Let F from X to Y be an invertible. Show that inverse of F inverse is F. See, inverse of F inverse is F. F inverse whole inverse is equal to F. Okay. It's there in the model question paper also. MQP. Even in the previous result, of course. Solution. Given F from X to Y be an invertible function defined by F of X is equal to Y. For all X belongs to capital X and Y belongs to capital Y. Therefore, there exists F inverse from Y to X defined by F inverse Y is equal to X is also invertible, because inverse of a bijective function is also bijective. Therefore, F inverse the whole inverse is equal to from set X to set Y. F inverse whole inverse from set X to set Y defined by F inverse whole inverse of X. F inverse whole inverse of X In place of f inverse whole inverse. F inverse whole inverse of x is equal to y. So that is nothing but, what is f of y actually? F of y is nothing but, f of y is nothing but, y is nothing but f of x. So therefore, f inverse whole inverse is equal to f. That means inverse of f inverse is f. And the fifth result, only statement, the inverse of a bijective function is also bijective. No proof, you just remember the result. Problems. First one, exercise problem. State with reasons whether the following functions are inverse. Following functions have inverse or not. Under that, number A, f from the set 1, 2, 3, 4 to the set 10, singleton set with f is equal to 1, 10, 2, 10, 3, 10, 4, 10. Okay. Clearly, f of 1 is equal to 10, f of 2 is also 10. F of 1 10, f of 2 is also 10. But 1 and 2 are not equal. F of 3, f of 4, both are 10. Again 3 and 4 are not equal. Distinct elements have distinct images, That's why it is not 1, 1 function. Not 1, 1 function. Observe the range of the function. Range of the function is 10 only. Range of the function is 10. And of course, codomain is also 10. So clearly, range of f is equal to codomain of f. Therefore, f is on 2. F is on 2. Since f is not 1, 1, f is not 1, 1, that means not bijective function. Hence, f inverse does not exist. F inverse does not exist. Number B, another function g from the set 5, 6, 7, 8 to the set 1, 2, 3, 4 with g is equal to 5, 4, 6, 3, 7, 4, 8, 2 they have defined. So clearly g of 5 is equal to 4, g of 7 is also 4, but 5 and 7 are not same. So g is not 1, 1, not 1, 1. Clearly, range of f is 2, 3, 4. Range of f is 2, 3, 4. But codomain is nothing but 1, 2, 3, 4. So range of the function g is not equal to codomain of the function g. That means g is not onto, hence g inverse does not exist. G inverse does not exist. So one of the important problem in 5 mark section again. Okay, in question number 39, part D, 5 mark section. Question number 3. Exercise problem. Consider the function f from set of positive real numbers r plus to closed interval 4 up to plus infinity, 4 to infinity, given by f of x is equal to x square plus 4. Show that f is invertible with the inverse f inverse of f given by f inverse of y is equal to root of y minus 4, where r plus is a set of all non-negative real numbers. R plus means set of all non-negative real numbers, nothing but positive real numbers. So it is appeared 4 times in 5 mark section: annual 2015, supplementary 2016, annual 2018 and supplementary 2018. Same year it is appeared twice. Solution. Given f from the function f from set of positive real numbers to 4 to infinity, closed interval 4 up to plus infinity, given by f of x is equal to x square plus 4, where x belongs to the domain R plus. Say some equation 1. Let f of x is equal to y. What is f of x? X square plus 4 is equal to y. Solve for x actually. So y minus 4 is x square. X is equal to root of y minus 4. So f from a to b means the inverse of f, let us say g from b to a. So assume g from b to a, g from b to a. The domain and codomain should be interchanged. G from b to a, that means closed interval 4 comma infinity to a positive real number defined by f of x equals y means x equals g of y, x equals g of y. But what is x actually? Root of y minus 4. So for all y belongs to codomain, y belongs to codomain of the function f, that is 4 comma infinity. Why? Because if you take less than 4, say 3 minus 4 means minus 1. So it is not a real number, becomes a complex number. Root of negative number is complex number, you know. That's why 4 to infinity. If you obtain this, you will get the first mark. Idikke 1 marks sigute. So the distribution is like this only. That's why I have written on the board. Now for all x belongs to R plus positive real numbers, that is domain. So domain means, so R plus, you need to operate the function f first. Gaf of x, x is a domain, you know, belongs to domain. Gaf of x can be written as g of f of x. Observe f of x. F of x is nothing but x square plus 4, you know, by using equation 1. This is of the form g of y. G of y means root of y minus 4. G of t means root of t minus 4. G of x square plus 4 means root of x square plus 4 minus 4 using 2. Plus 4 and minus 4 gets cancelled. Root of x square means x we are left with. Gaf of x is equal to x. Therefore, gaf is an identity function on the set of positive real numbers domain. Say some equation A. If you obtain gaf, you get another mark, 1 mark. Okay. And y belongs to codomain, that is closed interval 4 up to plus infinity. Closed interval 4 up to plus infinity. So fog of y, you need to operate g first. Okay. So f of g of y. What is g of y actually? G of y is using 2 root of y minus 4. This is just like f of x. Using equation 1, f of x means x square plus 4. F of this means this square plus 4. Square and square root gets cancelled. Y minus 4 plus 4. Plus 4 minus 4 gets cancelled. We are left with y. That means fog is an identity function on the codomain of f. That is a set of the set closed interval 4 to infinity. Say some equation b. So if you get equation A, 1 mark, equation B, 1 mark, identity function. Now from the equation A and B, equation 1 is gaf is identity function on R plus, fog is identity function on 4 comma infinity, closed interval. So from A and B, by definition of invertible function, clearly f is invertible with f inverse is equal to g. Operate y on both sides. F inverse of y is equal to g of y. If you write this conclusion from A and B, f inverse exists anta hellikkene 1 marks barate. If you don't write this conclusion, you will be deducted 1 mark. Okay, please note that. From A and B, after the conclusion, we have already the solution. Also write the inverse of f. So inverse, what we have assumed? G from 4 to infinity to R plus defined by f inverse of y. What is g of y? By using equation 2, it is root of y minus 4. G from b to a we have assumed, you know. So therefore f inverse is equal to f inverse y is equal to root of y minus 4 for all y belongs to codomain 4 to infinity. So to writing f inverse, one more mark, the fifth mark actually. You can write this in terms of x also. Instead of y, you can write in terms of x also. The fourth one, worked example, prove that the function f from capital N to y defined by f of x is equal to x square, where y is equal to the set of elements y such that y is equal to x square. Y is nothing but f of x, in which x belongs to natural numbers, is invertible. Also write the inverse of f. This is appeared in the year 2014 in 5 mark section. The same question can be asked like this. Let y is equal to the set of elements n square such that n belongs to capital N, is a subset of capital N. Consider f from n to y defined as f of n equals n square, f of x equals x square. In place of x we have n, f of n is equal to n square they have defined. Show that f is invertible. Find the inverse of f. So either this or this, both are one and the same. Solution. Let capital Y is equal to n square. Let us discuss in terms of n. Capital Y equals n square such that n belongs to capital N, is a subset of n. Also f function f from n to capital Y defined by f of n is equal to n square for all n belongs to capital N. Say some equation 1. Let f of x equals y, we take here f of n is equal to y. What is f of n? N square is equal to y. So that n is equal to root y. So now f from n to y, now the inverse of f, let me take it as g. Let us assume that as g. G from b to a, that is y to n. G from y to n defined by f of y is equal to n. I mean g of y is equal to n. G of y is equal to n. N is nothing but root y. Say some equation 2 for all y belongs to capital Y. This carries, if you write the equation 2, you will get 1 mark. If you assume the inverse function like this, you will get 1 mark. Now for all n belongs to capital N, that is the domain, gaf of n is equal to g of f of n. Observe f of n. F of n is nothing but n square, So g of n square. This is of the form g of y. G of y means root y. G of t means root t. G of n square means root n square. Square and the square root gets cancelled. That means gaf of n is equal to n. Therefore, gaf is an identity function on the set n, domain of the function f. Say some equation A. So this carries another mark. Okay. Also, for all y belongs to capital Y, codomain. Now, fog of y is equal to composition of g and f is equal to f of g of y. Look at equation 2. What is g of y? Root y, This is just like root f of x. Using equation 1, f of x is what? X square. F of root y means root y the square. Square and the square root gets cancelled. We are left with y. Fog of y is equal to y. Therefore, fog is an identity function on the set capital Y, codomain. Say some equation B. This carries 1 more mark. The third mark, let us say. Okay. So till this you get 3 mark only. Okay. So after writing the conclusion from A and B, identity function on the set A domain, this is fog is an identity function on the set B. B is codomain. If you use the definition, clearly f is invertible. with F inverse is equal to G. So that is operate Y, F inverse Y equals G of Y. So that carries one more mark. Okay. So we have assumed G from Y to N defined by F inverse of Y is equal to G of Y using equation 2. G of Y is root Y, for all Y belongs to capital Y. This gives the last mark. This fetch you the last mark. That is the fifth mark. This is how the distribution is. The fifth one, an exercise problem. Prove that F from N to Y defined by F of x is equal to 4x plus 3, where capital Y is equal to the set of elements Y such that Y equals 4x plus 3. Y is F of x, in which x belongs to natural numbers, is invertible. Also write the inverse of F. Annual 2014, it is appeared in 5 mark. It is almost same as the second question. So same as the second question only. Given F from N to Y defined by F of x is equal to 4x plus 3. Say some equation 1 for all x belongs to the domain. Now let us assume F of x is equal to Y. What is F of x actually? 4x plus 3 is equal to Y. 3 to the other side, 4x equals y minus 3. Solve for x means divide by 4. X is equal to y minus 3 divided by 4. Now assume G from B to A. F from A to B means inverse is G from B to A. That means y to N defined by G of y is equal to x. G of y equals x. But what is x actually? Y minus 3 divided by 5. So G of y is equal to y minus 3 divided by 4 for all y belongs to capital Y. Thus fetch you the first mark. Okay. Now for all x belongs to N, that is domain, Gauss of x is equal to G of F of x. What is F of x actually? By using equation 1, 4x plus 3, using equation 1. Now observe, this is just like G of y. G of y means y minus 3 by 4. Similarly, G of t means t minus 3 divided by 4. G of this means 4x plus 3 minus 3 divided by 4. Plus 3 minus 3 gets cancelled using equation 2. So 4x by 4 means 4 gets cancelled. That means Gauss of x is equal to x, an identity function on the set domain, natural number. Say some equation A. This carries the second mark. And for all y belongs to capital Y, that is a codomain, fog of y is equal to f of g of y. That is f of, what is g of y? Observe the equation 2. So that is y minus 3 divided by 4 using equation 2. This is of the form f of x. F of x means what? Using equation 1, 4x plus 3. F of t means 4t plus 3. F of this means 4 into this plus 3. 4 gets cancelled. Y minus 3 plus 3 means again 3 gets cancelled. Fog of y is equal to y. Therefore, fog is an identity function on the codomain, that is capital Y. Say some equation B. For equation B, the third marks you get. Now write the conclusion. From A and B, from the equation A and B, Gauss is identity function on the set N and fog is identity function on the set Y. So clearly F is invertible with F inverse is equal to G. Therefore, F inverse of y equals G of y. So for writing this conclusion only, you will get one more mark. 4 marks we obtain. So finally you write the answer. Therefore, G from y to n defined by F inverse of y, F inverse is nothing but G only. G of y is what? From equation 2, y minus 3 divided by 4 for all y belongs to capital Y. So we have assumed G as y minus 3 by 4. So but not yet confirmed. Now after showing A and B, so by definition it is invertible. That's why F inverse of y is equal to y minus 3 divided by 4. That gives the last mark, I mean the fifth mark.